we start from the number line, the very basic stuff. Now look at the screen. You just remember a number line has three components. A number line has three components. A unit of length, a fixed point is called the origin, and a positive direction. Again, a number line has three components. I will show you the meaning on PowerPoint. Okay. You do not need to copy the stuff on the screen. So this thing is on the course manual. I'm making my point. A number line has three components: a unit of length, a fixed point, and a positive direction. You're so familiar with this. A number line is something like this, right? You're given a positive direction, a fixed point. A fixed point is called the origin. The origin, we label the origin using O. Okay, using O. Or alternatively, you can imagine the origin is 0. Okay. Actually, the origin is representing the number of 0. And the unit of length, you're so familiar with this. So by that we mean you need to give a point representing 1. Three components: the origin, a unit of length, and a direction. Okay. After setting up a number line, after setting up a number line, then the main thing is, now listen to me carefully. I'm talking about the main thing. There's a one-to-one correspondence. Between the real numbers and the points on number line. By that we mean each real number is represented by a point on the number line. Each number is represented by a unique point, one and only one point on the number line. On the other hand, each point on the number line represents a unique number. That's why I said there's a one-to-one correspondence between the points on number line and the points and the real numbers. The points I was trying to make in here. Now look at the mouse cursor. Every point on the real number line is represented by a unique real number, and the other way around. Conversely, every real number is represented by a unique point. Okay, so now let's say if I give you a number, let's say I give you a number 2, that's a real number. Okay. After setting up the number line, 2 is represented by one and only one point on the number line. Now let's say here, right? On the other hand, if I give you a point, the point represents a unique real number on the number line. So do you want to write something in the chat? So anybody want to tell me the number represented by this point? On the number line, we just mentioned every point represents one and only one number. Now I'm looking for a number represented by this point on this number line. Yeah, I think I was trying to do -1. So -2 is okay. I think I was trying to draw -1. Probably -1 is right. Okay. Okay. Again, but there's we say there's a one-to-one correspondence between the two things. One thing is that the numbers on the real numbers. The other thing is the points on the number line. There's a one-to-one correspondence. Easy. You know this a long time ago. You have seen this all the time. After setting up after talking about the number line is a one-dimensional stuff. So later on in this course, you are going to have way better understanding of what we mean by dimensions. And then we go higher dimension. Higher dimension, we talk about coordinate plane. Some people call it a rectangular coordinate plane or Cartesian coordinate plane. Cartesian is a name. Rectangular coordinate plane. It's formed by two number lines. It's formed by two number lines. Okay. In most cases, the setup is something like this. You use this all the time. I'm talking about this case. Okay. You have two number lines. One number line, we call one number line the horizontal axis. Okay. The other number line is the vertical axis, or x-axis and y-axis. Okay. And the two number lines, they meet. The point of intersection is the common origin. Again, you have two number lines. Okay. One is drawn horizontally in most cases. The other is vertically. Okay. The point O is the common origin of the two number lines. If you have two number lines setting up like this on the plane, okay, we call the whole thing. So basically, a plane equipped with two number lines meeting at the origin is called a rectangular coordinate plane, or Cartesian coordinate plane. I will write Cartesian. Okay, Cartesian. It means Cartesian. Cartesian. After setting up a rectangular coordinate system, or rectangular coordinate plane on the rectangular coordinate plane, there's also a one-to-one correspondence thing. Okay, now listen to me carefully. Okay, every point on the rectangular coordinate plane is represented by a unique ordered pair of real numbers. We call them the coordinates. Okay, we have two number lines. We mentioned the direction, we mentioned the origin. Now let's say the unit of length on x-axis is here. Now let's say the unit length on y-axis is here. And by the way, the unit of length on the two axes, they don't have to be the same length. They don't have to be the same length, I'm trying to say. Okay. Now let's say the unit of, now let's say 1 on vertical axis is here. Okay. I'm trying to make my point now. Okay. Every point, there's a one-to-one correspondence between the points on the plane and the ordered pair of real numbers. By that we mean their coordinates. Okay, I'm making my point. Every point on the plane is represented by a unique ordered pair of real numbers. I said ordered pair. Okay, so now let's say if I give you a point here, you just think about their coordinates. Okay. If I give you a point here, now let's say anybody want to tell me the ordered pair representing that point? By that we mean we're looking for the coordinates of this point. Okay. The ordered pair, now let's say x coordinate is 1, right? And the y coordinate is, I was trying to make the y coordinate of 2. Now let's say on vertical axis 1 is here. I was trying to make this point having the y coordinate of 2. I said ordered pair of real numbers. I said ordered pair of real numbers. Ordered pair of real numbers. I just wrote reals. So because 1, 2 and 2, 1, they represent two different points. Okay. 1, 2 is here. The point with x coordinate of 1 and y coordinate of 2 is here, right? And the point 2, 1 is at a different location. 2, 1 is here. You have seen this all the time. So basically, we are going to generalize this to higher dimension. We are going to talk about three-dimensional space, 3 space, very shortly. Okay. That's a point with coordinates of 2, 1. It's nothing too complicated, so we just did not use the term. Now I'm trying to say ordered pair of numbers. In all this, we have always been saying so is their coordinates, the coordinates of the point. Okay. And conversely, the other way around. Conversely, the other way around. If I give you a ordered pair of real numbers, a ordered pair of real numbers corresponds uniquely to a point on the plane. Okay. Now let's say if I give you a ordered pair of real numbers, so something like the first number x, kind of say x and y coordinates. If I give you a point with if I give you x coordinate is 1 and y coordinate is -1, this pair of real numbers will determine a point on the rectangular coordinate plane uniquely. Okay, so the point is determined by something like this: x coordinate is 1, y coordinate is -1. You have a point in here, right? It's nothing but the coordinates we have learned, we have been using all the time. Okay, now I will show you the screen again. Okay, after setting up a Cartesian or rectangular coordinate plane property, every point on the plane, now look at the mouse cursor, is represented by a unique ordered pair of real numbers. It means their coordinates. Okay, and on the other way around, conversely, every ordered pair of real numbers represents a unique point on the plane. Easy, right? I think I made my point. I think the question on the screen is super simple. I do not have to make too many comments on that. I give you a pair of numbers, you can determine a point. Right? Now we're going to go higher dimension. We're going to talk about three-dimensional space. Yeah, probably in high school you haven't seen anything like this before. Okay. Likewise, we have three axes: x-axis, y-axis, and the z-axis. They share the same origin. In most cases, they have the same unit of length, but they don't have to have the same unit of length. They share the same origin. Okay. The direction. I will show you the meaning. Okay. So temporarily, you look at the screen. X-axis is backward, from inside to outside. Y-axis is rightward, the general setup. Y-axis is rightward, from left to right, the direction. And Z-axis or Z-axis is upward. I will make some comments on that. Okay. In most cases, we give the setup like this. You imagine everything in space, in 3D. Okay. That's y-axis. They share the same origin. You have three number lines. They share the same origin. Now let's say the origin is here. The origin O is here. Okay. X-axis is from inside to outside. I cannot draw it actually from inside to outside. You imagine the stuff in space, in 3D. That's x-axis. And the z-axis is upward. It's upward. Z-axis is something like this. The three axes are perpendicular of each other. Okay, are perpendicular each other. Again, x-axis is outward. So can you see it's from inside to outside? It's outward. And the y-axis is rightward, from left to right. Z-axis is upward. That's the setup. In most cases, that's the setup. Actually, okay, now I want you to get your right hand. Get your right hand. The setup is consistent with the right hand rule. Okay. I think for the people in physics, you have seen this all the time. There are many things satisfying the right hand rule. Okay. The torque, probably you learned that in physics, and many other things. I don't remember too many. But now get your right hand, please. Use your right hand only. Use your right hand only. Do not use left hand. Okay. Okay. Now I want you to use your thumb to point in the direction of x-axis. Use your index to point in the direction of y-axis. And your index and your middle finger should be in the direction of z-axis. Okay. I'll see if I can turn on the camera to show you. Can you see me on the camera? No, it's sorry, it's my. That's not my real camera. MSI, I forgot. I think I need to press some key to turn on the camera. I forgot the key. Sorry, I cannot show you that today. So maybe next time. Okay. But now let's imagine. Your again. I want to repeat. A thumb in the direction of x-axis. Index in the direction of y-axis. And then your middle finger should be in the direction of z-axis. So in general, that's the setup of the xy and z axis. I mean. So do you have any questions? You can type in any questions. Do you have any questions? If you have any questions, I can. Give me a little moment. I'm looking at my keyboard. I think F6 is probably the way to turn on the camera. It doesn't matter now. You just remember the direction for now. So later on, when we talk about the cross product, I promise I'll figure out the way to turn on the camera. I'm using MSI, so they think it's a little weird. Okay. In most cases, we just remember x is outward, y is rightward, and z axis is upward. Okay. So don't worry. The same as before. After you have a rectangular coordinate system in space, we call the whole thing a Cartesian or rectangular coordinates in space. Then every point is represented by a unique triple of real numbers. We call them x coordinate, y coordinate, and z coordinate. And the other way around is also true. I give you three numbers in order, then you can determine a unique point. Okay. I will show you a little picture in here, how to get the coordinates of the point. Okay. Now look at the screen. So look at the mouse cursor. Now let's say I give you a point. You imagine I give you a point P in the space. Now I'm talking about how to determine the coordinates. Now, this time I'm going to give you a more detailed description. Okay. P is a point in space. Now follow my mouse cursor. You have a P in here, okay? Now look at P. P is a point in space. Then how can we determine the coordinates? How can we determine x coordinate? How can we determine y coordinate? How can we determine z coordinate? Now listen to me carefully, okay? Passing through this point P, you draw a plane perpendicular to x-axis. Listen to me carefully. Passing through this point P, you draw a plane perpendicular to x-axis. There's a point of intersection. The plane and the x-axis, the line has a point of intersection. That point on x-axis has a coordinate, right? Every point on number line corresponds to a number. This number is x-axis. In this case, x coordinate is 2. Okay, that's why you have x coordinate of 2. Imagine everything in 3D, in 3 dimensions. Okay. Likewise, passing through this point, you draw a plane perpendicular to y-axis. There's a point of intersection on y-axis, and then this point on y-axis has a coordinate representing a number. That's the coordinate. That is a y coordinate. Okay, and likewise you have z coordinate. I'm trying to say every point in the space, actually in the Cartesian coordinate space, it corresponds to a unique triple of real numbers. These 3 numbers are called x coordinate, y coordinate, and z coordinate. That's one way of the story. I give you a point, you can get the coordinates. The other side of the other way around is I give you 3 numbers, I give you the coordinates, and then you can uniquely determine a point. That's what we meant by every point in the coordinate space, rectangular coordinate space, is represented by a unique triple of real numbers: x coordinate, y coordinate, and z coordinate. So likewise, the other way around, every triple of real numbers, if I give you x coordinate, y coordinate, and z coordinate, then I'm reading Tyler's question. So to find the point of coordinate, I'm not sure if I fully get your question, but I think it's true. So basically, to say this story, if I give you a point, it's okay as long as you know how to get the coordinates of the point. It's okay. The other way around, if I give you 3 numbers, now let's say 1, 2, 3, you can just imagine the point in the space. Yeah, it's kind of that. I think it's true. In many cases, it's hard to draw. You need to imagine the location of the point. Actually, where it's possible in math, in this course, to talk about n-dimensional space. So later on, you are going to have way better understanding of what we mean by n-space, what we mean by the dimension. Actually, we are going to define the dimension very precisely later in the course. Okay, when we talk about the general vector space. Any other questions? Okay. A very useful tool to study n-dimensional space, n-space, or 3-dimensional space, and even 2-dimensional space are vectors. Now look at vector is actually a key concept in this course. In the rest of the course, we are going to see vectors over and over again. Actually, that's the main object studied in this course. It's kind of like functions in calculus. If you did calculus, if you are taking calculus, functions are the main objects studied in calculus. I told you before, right? It's kind of comparable to that. Vectors are kind of the objects studied in this course in linear algebra. Okay. Now let's define what we mean by vectors. Okay. Actually, why we introduced the concept of vectors? In many other sciences, actually now let's talk about something in physics. At least you learned some physics in high school. Vectors, we use vectors to represent quantities with both magnitude and directions. Okay. In physics, you learned velocity, even the displacement, velocity and force are all the quantities having both magnitude and directions, right? So these are the quantities that can be represented using vectors. I'm pausing for people who have not taken physics for a long time, but I think you can imagine. So now let's say a force. You push something. You could push something in different directions. Okay, force as a magnet. Force also has a magnitude. Okay, you push it harder or lighter. In any case, in physics, we have many quantities with both magnitude and directions. So these things can easily be represented using vectors. Okay. Now I'll show you the definition of vectors. We are going to define in two ways. One way is geometrically. Okay. A geometric vector is a directed line segment. We use a directed line segment to represent a vector. Okay, in most cases we imagine the vector as in a rectangular coordinate plane or space. Okay. So now let's say a vector, it can be something like this. So can we talk about the stuff on rectangular coordinate plane? We're going to talk about two-dimensional case. Okay. A vector, it can be something like this. Okay. We use a directed line segment to represent a vector. A directed line segment has a direction. The direction is for the direction of the vector. Okay. And we use the length of the directed line segment to represent the magnitude. Okay. Again, you just remember a vector mathematically, so geometrically, is represented by a directed line segment. It can also be something like this. Okay. We use uppercase letters to label the points. So now let's say if I use A to label this point, we call this point an initial point. Okay. A directed line segment represents a vector. A vector has an initial point. Now let's say in this case, I use A to represent the initial point of that vector. So look at the mouse cursor. Okay. And the B is called the terminal point. I was trying to write B. A directed line segment represents a vector. A vector has an initial point, a terminal point. Okay. If I want to write a vector using one letter, you can represent the vector using the notations like so now let's say V, the most commonly used notation, or U. Okay. I'm trying to say if you represent the vector using one letter, you write a lowercase v or u. v, w. So these are commonly used notations for vectors. Okay, and then you write an arrow on top of v. I think some people also write a vector something like this. But in the future, in this course, we agree to use arrow to represent a vector. We say vector v. Or alternatively, you can represent a vector v, so something like this. You use the initial point and terminal point to represent a vector. Okay. This notation, the circled notation, is for the vector with the initial point of a and terminal point of b. We're going to use both ways. We're going to use both ways to represent a vector. Okay, depending on which way is easier in different contexts. Okay. We just mentioned a vector has an initial point, a terminal point, right? And on rectangular coordinate system or Cartesian coordinate system, so by that we mean a plane or a space equipped with Cartesian 3 axes or 2 axes. Okay. If the initial point is the origin, then we call the vector a position vector. Okay, I'm not going to repeatedly using the notations. So can I call this point C? This is the standard notation for the origin. Okay. I'm going to call this vector U. Now look at the screen. On the screen you have a vector U. U is also represented using OC, right? You specify the initial point. The initial point is O, the terminal point is C. Okay. This vector is a position vector. A position vector, again, I'm going to repeat the definition. A position vector is a vector in which the initial point is the origin, O. Okay. So we have a position vector. Eventually, we are going to connect vectors with numbers. We are going to use some numbers to represent the vector. But before that, we need to define what we mean by two vectors are equal. So this is important. Now remember the definition. The definition is here. Now follow the cursor. Follow my mouse cursor. Okay. Two vectors are equal. Geometrically, two vectors are equal if they point in the same direction and have the same length. I'm going to repeat the definition. Okay. So geometrically, it's super important to know what we mean by two vectors are equal. I do not care their initial point and terminal point, as long as the two vectors they have the same direction, they point in the same direction. There's a typo here. Remove that S. They point in the same direction, and they have the same length, and then the two vectors are equal. I will show you what I mean on PowerPoint. Okay. Now let's say, so geometrically you have a vector, so now let's say V, something like that. You have another vector U, something like this. Use your common sense to understand what we mean by the two vectors point in the same direction. I was trying to draw two vectors point in the direction of, can I say, southeast. Southeast is I believe you know what I mean by southeast, right? Upward is north, and rightward is east, I believe, right? If the two vectors are pointing southeast and having the same length, these two vectors are equal. geometrically they are equal. Again, I do not care they have their initial points and terminal points, as long as they point in the same direction and having the same length, they are equal. So in this case, we have two equal vectors. So vector u is equal to vector v. If you are in physics, so this is very much consistent with what you define in physics. I think for the people in physics, so they think it's too simple probably. Okay. I just told you what we mean by two vectors are equal. Okay. After that, we are ready to talk about how to represent a vector by numbers, actually by a pair of numbers. It's comparable to what we did earlier. Okay. Each point, so now let's say each point on the rectangular coordinate plane can be represented by a unique ordered pair of numbers. Okay, so we can connect the numbers to points. Points are something so geometric. Numbers are something algebraic, right? We can make the connection. And likewise, now we are going to represent vectors using numbers. Actually, we are using components of a vector. We are using two numbers. We call the two numbers the components. Now we are going to define that right now. Okay. Okay. Now let's look at the screen so that I'm not going to lose track. Okay, now I'm going to talk about this part. Okay, it's ugly. It's a little ugly to highlight that. So just read the first paragraph. The first sentence in that paragraph. The third paragraph. Okay. The first thing we do is to represent a position vector. The first thing we do is to represent a position vector. Okay. Now listen to me carefully. I'm going to make my point. I know for today's class, so there are too many basic concepts. Okay. But I think you have seen most of these before. Okay. Again, now I'm going to represent a position vector using numbers. Okay. Now let's say you have a position. The definition of a position vector is a vector with the initial point, the origin. Now let's say the terminal point is the point 1, 2. The terminal point is the point with x coordinate of 1 and y coordinate of 2. Okay, so that's the point 1, 2, right? Can I use a letter to represent the point? So now let's say I'm going to use A to denote that point. Okay, A has x coordinate of 1 and y coordinate of 2. So by the way, I'm talking about two-dimensional case. The same is true for three-dimensional case. Okay. Now we can talk about a position vector with initial point of the origin. A position vector is a vector with initial point of the origin, right? Now let's say the initial point is the origin O, the terminal point is the point A. So geometrically, a vector is something like that. Illustration only. Sorry, it's hard for me to draw it straight. Now I'm going to. So you have a vector OA. OA is a position vector. Okay. Now this position vector, I'm going to represent the position vector using the coordinates of the terminal point of the vector. By that we mean I'm going to represent OA using a ordered pair of real numbers. The first number is 1, the second number is 2. But we write the two numbers in column. We call them components. Listen to me carefully. I'm talking about the term, the name, the terms. If I'm trying to use numbers to represent the vector of A, I'm going to write the two components, the two numbers. The two numbers are coming from the coordinates of the terminal point A. So because the initial point has to be 0, 0. Okay. So as long as you have the terminal point, then you can the terminal point uniquely determines a position vector. So can I say that way? And then after you have the coordinates of the terminal point, then you write the two numbers in column in order. Okay. So that's the x coordinate of the terminal point A. That's y coordinate of the terminal point A. That's how we represent a vector. Again, when representing a vector, we write the numbers in columns. Also, the terms are different too. The names are different too. When talking about a point, we say 1, the x coordinate. We say 2, the y coordinate. When talking about vectors, we say 1, the first component. We say 2, the second component. So basically, these two numbers, when talking about the vectors, we call them components. Okay. I'm going to give you the name. Okay. This one is called the first component. Components. So this number is called the second component. Okay. Any questions so far? So we know how to represent a position vector already. Okay. After learning how to represent a position vector, then we can talk about how to represent any vector. Okay. How to represent any vector. To represent any vector, so okay. Now let me try to draw something. Okay. Now, so how about I'm going to use a particular question to tell you how to represent any vector. Okay, how to represent any vector. So now let's say you have a vector. Now let's say you have one. I was trying to. The origin is here. X-axis here. Actually, in old days, I used to require people to draw everything properly. Okay. To label x-axis, to label the directions, to label the origin. Now I'm losing the requirement on that. As long as you know what's going on, it's fine. Okay. Oh, okay. Now let's say you on vertical axis you have a point. So now let's say 1 is here, and then 2 is here. So can I get one more point? So maybe 3 is here. You have 3 here. Okay. Now let's talk about a simple vector. A simple vector with the initial point A. A has x coordinate of 2, 2, and y coordinate of x coordinate of 2 and y coordinate of 2. That's what I meant. Okay. Now let's say you have another point. Initial point A is A. Okay. A terminal point. So now let's say it's B. B has the coordinates of 2, 2, 3, 3. I mean. Okay. I'm trying to say B has x coordinate of 3 and y coordinate of 3. Okay. I said A is the initial point of the vector, B is the terminal point of the vector. So these 2 points determine a vector. Now let's say the vector from A to B. A proper notation is something like this. The vector from A to B, you represent the vector from A to B. If you know the notation of the initial point and the notation for the terminal point, a vector from A to B is represented by something like this, right? I'm keeping on repeating the meaning of the notations. Okay. Now I'm trying to represent the vector AB using components. Earlier we just learned how to represent a position vector. Okay. So does that make sense? We also mentioned what we mean by two vectors are equal. Now let's recall two vectors are equal if and only if they point in the same direction and they have the same length, right? What we do now we want to represent the vector AB, that vector. We have already seen how to represent a position vector. Now all we need, I hope it makes sense. All we need now is to find a position vector that is equal to AB. I want to repeat, all we need is to find a position vector that is equal to AB, the vector AB. We know how to represent the position vector, so we know how to represent AB. Anybody want to tell me how to represent AB? So later on you are going to have formula, but now I want you to tell me how to represent vector AB using the definition. As long as you know that, then you know what we mean by equal, by two vectors are equal, you know the definition. Anybody want to tell me the representation of AB? So just write the two numbers, two components. So please tell me the two components, please. Please, anybody? To represent, yeah. Try again. So anybody else? Try again. You know the initial point, you know the terminal point. So this time I want you to, it's kind of moving this vector to the location of a position vector. So you know how to represent the position vector. Try again, please. Anybody? Okay. I think one is right. One is right. Okay. Now let me tell you what I mean. Okay. What do we mean? To represent the vector AB, we are looking for a position vector that is equal to AB, right? We are looking for a position vector that is equal to AB. So right? It's kind of, you want to move this vector so that do not change the length and the direction. You want to move this vector, do not change the length and the direction, so that the initial point is at the location of the origin. That is the vector which is equal to the vector AB, right? That's how you get a vector equal to vector AB. So that makes sense? You get a vector equal to AB. I believe the vector is something like this. So maybe my drawing is not too perfect, but I'm showing you my point. Move this vector so that the initial point of the vector AB is at the origin, and then you know how to represent this vector, right? Okay, can label this point using C. I'm trying to say AB is equal to OC. OC is a position vector. Okay, we have learned how to represent OC. C has the coordinate, so in this case 1, 1. That's how you can represent the vector AB. So that makes sense now? So don't worry. So very shortly we are going to have a formula for computing the components of the vector if you know initial and terminal points. But now, still I want to see that using the definition. Any questions on this? At the beginning we learned how to represent a position vector. Now we can represent any vector. All we need is to make any vector a position vector by moving around, right? I hope it makes sense now. Okay. We did many definitions. Yeah, probably it's time to talk about some questions. One more One more thing I want you to see. One more thing I want you to see. And so before we do some questions, okay. I want you to follow the mouse cursor, okay? To look at this part, okay? Every vector has a representation now, okay? You just move the initial point to the origin. You can represent the vector. Now I want you to see that conclusion is true. Two vectors are equal if and only if algebraically, okay? If and only if they have the same components. No matter how you move around, they have the same components, right? And also in the future we use R2 to denote the collection of all the two-dimensional vectors. I know in high school probably you learned you use R2 to denote all the points, okay? But vectors are way better tool to study many properties in two-dimensional or three-dimensional cases. Now in this course we're going to use R2 to denote the collection of all the two-dimensional vectors. Actually, we rarely talk about points in this course. Okay, I know too many definitions, but after doing a few questions, then you should be able to be okay. So, but before we talk about before we do the handout questions, now I want to tell you a conclusion. Now look at the theorem on the screen. The theorem on the screen. It shows you if you know the initial point, if you know the terminal point, then you can represent the vector using two components. The components can be computed that way. Okay. I will show you the meaning of the formula. Now concentrate on that formula first. So this one is for the two-dimensional case, and after you know the meaning of the two-dimensional case, it's easily generalize the formula to the three-dimensional case. I will show you what I mean, okay? So how about we just talk about this question, okay? I told you how can you possibly get the two components, and I told you, so don't worry if you do not fully get this. We have a formula to compute the components if you know the initial point and terminal point, okay? Now I'm trying to represent the vector AB in terms of using its components, using the components, okay? Okay, for point A, I'm trying to make the notations consistent with the notations in the theorem, okay? For point A, I'm going to use x1 to denote the x coordinate of initial point. I'm using y1 to denote the y coordinate of the initial point. I think I said it right. And for B, I'm using x2 to denote the x coordinate of the terminal point. I'm using y2 to denote the y coordinate of the terminal point. The conclusion tells you the components of the vector with initial point p1, terminal point p2 is computed using that formula, right? Now look at the formula again. The first component is the difference between two x coordinates. The second component is the difference between two y coordinates, right? You know that. Okay. So in this case, initial point is A, terminal point is B. So the representation is how do you get the first component? The difference between x coordinates, 3 minus 2. Okay. Now remember, use the x coordinate in terminal point first, okay, and then minus the x coordinate of initial point. And the second component is also 3 minus 2, right? So this time you compute the difference between two y coordinates. So that's how you get 1, 1. Now it's easy, right? Now we have a formula to compute. Again, that formula is used to compute the components of a vector if you know the coordinates of initial point and terminal point. And not too many definitions, too many basics. Now we're going to do some questions to get you over the concept. Okay. We'll work on the questions one by one. Okay, now let's look at the question. We'll work on the questions one by one. In the question, I give you a vector u. U is a vector from point A to point B. Okay, so in any case, you need to get the initial point and terminal point. Yeah, probably I can. Yeah, so I can have coordinates. So can I use that way? Okay. That's my x-axis. Now let's say my y-axis is here. Probably I can find a way to draw straight lines, but I think it's okay. You know the meaning. Okay, now we're trying to sketch the vector u. U has the initial point of a. A has x coordinate of -2 and y coordinate of 3. Okay. -2 is here. Sorry, the grid may not be too good, but so can I make this point 1, this point 2, this point so -1, this point so -2. Okay. In any case, I want you to sketch the points. Okay. And so on. Okay. A has x coordinate of 2 and y coordinate of 3. I think x. Yeah, that's the point in here. That's point A. A has x coordinate of -2 and y coordinate of 3. And B is the point with x coordinate of 1 and y coordinate of 5. I'm scared of that 5. X coordinate of 1 is here. I was trying to make this point 4. I think I was trying to make this point 5. I can see 5 now. 1, 5, I believe, is a point, so somewhere in here, right? So that's the point B. In question A, I wanted you to sketch the vector u. U has the initial point of A and terminal point of B. 1, 5 here. In question A, I just want you to draw u. U is a vector something like this. You label this vector using u. Okay. So we're done question A. Easy, right? You sketch the initial point, you plot the terminal point, and then you connect 2 points. You can have the vector. And then in question B, I want you to sketch the position vector u. I give you the 2 components. Sorry, so that's v. Okay, I want you to sketch the position vector v. V has 2 components, 3, 2. Okay. Now let's say 3 is here, 2 is here, right? We're trying to sketch the position vector. Position vector, now let's recall the definition. A position vector is a vector with the origin as its initial point. That is the vector v I wanted you to sketch. Okay, just label the vector v in here. Okay. Okay, now the main thing is try to answer the 2 questions. Are u and v equal? Explain geometrically. So anybody want to write the answer? I think I can tell you the answer is yes. And then explain how do you want to tell me why the 2 vectors are equal? Geometrically. Mention 2 things using the definition. They point in the same direction, right? They're kind of pointing in the same direction. That's one thing. The other thing is they are equal in length. They have the same length. Yeah. Mention 2 things. They have the same direction and the same length. Yeah. Mention 2 things. When you try to answer why the 2 vectors are equal geometrically. Okay. And in D, we're trying to write u in terms of ordered pair of real numbers. So by that we mean I was trying to ask you to compute u, to write u in terms of the components. Okay. Initial point is A, terminal point is B. Now we're going to use the components. We're going to use the coordinates of the 2 points, initial point and terminal point, to get the components of u. So that's my intention. Okay. The first component is computed using the difference between 2 x coordinates. Terminal point, x coordinate of the terminal point minus x coordinate of initial point, right? And likewise x coordinate of the to get the second component, you use the y coordinate of the terminal point, using terminal point first. Okay, 5 minus y coordinates of initial point. I think you end up with sorry, I forgot to label the terminal point here. I think the terminal point here is 3, 2. Right. I think the first component is 3. 1 minus -2, you have 3, right? 5 minus 3, you have 2. That's the answer to question D. Can I ask you one more question? Yeah, probably the question, I forgot to copy the question. No, I forgot to ask the question. Okay. Algebraically, anybody want to tell me why the 2 vectors are equal? We have seen why 2 vectors are equal, so geometrically. I'm going to add one more question, okay? And then you can tell me the answer now, okay? So explain why u is equal to v algebraically. They have the same components. Yeah, they have the same order pair. Yeah, that's the same thing, but we're, yeah, components. algebraically, we mentioned that two vectors are equal if and only if they have the same components. You see they have the same components, right? In question D, U have the vector U has the components of 3, 2. The position vector V also has the same components 3, 2. Yeah, that's why the two vectors they have the same components. Okay, so now I'm going to write the answer to E. Okay, U is equal to V. So because they have the same components. I did not write the answer to C. You just mentioned they have the same length and they are in the same direction. Okay. I hope using a question like that you have a little better understanding of how to represent a vector using components, how to see two vectors are equal, both algebraically and geometrically. Okay. I was trying to say something I forgot earlier. Yeah, now I remember what I was trying to say. Okay. If you read some other textbook, some people also write the components in rows, but most people write the components of a vector in column. So don't be too surprised if you see people write components in rows. That's also a common notation. It's kind of confusing to me, so because you don't know the two numbers represent the coordinates or vectors, right? Again, so most people write the components in columns. Any questions on this? Should be simple, right? Simple. I don't like the grid lines. Okay, for the second question, we're going to represent all the vectors using components. Can I label the vectors using starting from? Okay, I still prefer to use V for vectors. I'm going to make this thing a little bigger. I'm going to call that vector V1. I'm going to call that vector V2. I'm going to call that vector V3. I'm going to call that vector V4. Okay. I will show you how to represent V1. Then you tell me the answers to other vectors. Okay. To represent V1, actually the question is designed for the formula. If you know the initial point, if you know the terminal point, then you can have the representation of the vector. Okay. For V1, the initial point is the point with x coordinate of 1, y coordinate of 2, right? The terminal point, I believe, is 3, 3. As long as you know the coordinates of the initial and terminal points, then you can represent V1 in terms of components. The first component is computed using, now remember to use the terminal point first. Okay, the x coordinate of the terminal point minus x coordinate of initial point, which is 3 minus 1, I believe, and then y coordinate of the terminal point minus y coordinate of initial point. I think the representation of V1 is, I was trying to write V1. We represent V1 in terms of components as 2y, right? First component is 2, y. Second component is 1. Okay. I did V1 for you. Now I want you to, I will give you a few minutes, so maybe 2 or 3 minutes to get the representation of v2, v3, v4, and then we compare answers. Okay. So please, I want you to work on this one yourself. Represent v2, v3, v4. I do not want you to copy. I want you to work on it, and then we compare the answers. Okay. Anybody see a different answer? I hope I got everything right. Anybody want to correct me on something? Or confirm I have everything right? I think I have everything right.
Yeah, that's correct.
Okay, sure, thank you. Cool. I think the question should be simple. As long as all we need is to get the coordinates of initial point and terminal point. And then you use the formula, you can get the components, right? Again, no matter where the vectors are located, as long as they are in the same direction and having the same length, they are equal. For equal vectors, they have the same components, the point. All these questions are designed for that purpose. Okay. Actually, the same is true for vectors in space. If you want to look at the formula, the similar formulas are true for vectors in space. It's weird. I don't have a button to hide this. I have to do something else. Okay, now look at the formula for the vectors in R3. Again, R3 is the notation representing the collection of all vectors in the collection of all the vectors in the space. Every point in the space has three coordinates: x coordinate and y coordinate and z coordinates, right? As long as you know the coordinates of the initial point and terminal point, then you can represent the vector in terms of three components. A vector in space has three components, right? I think it's not too hard to imagine. After that, then we are going to practice a few questions. We're just following the handout. Okay. The two questions are similar, so we just do 3b. So that's okay. We just do 3b. Okay. This time for three-dimensional stuff, for the vectors in space, we do not draw sketch. But I really hope you can imagine the location of the points and the location of the vectors. The vector AC is initial point is A, terminal point is C. The question should be simple, right? The standard notation is AC. We use AC. You write arrow on top to indicate the point, the vector with the initial point A, the terminal point C. Okay. And then the formula, you look at the formula. Okay. You just subtract the corresponding coordinates, and then you have the components. Now remember to use x coordinate in point C, x coordinate for point C minus x coordinate for point A first. Okay. So by that we mean 2 minus negative 2, right? And then negative 3 minus 3. I think I got this right. And then negative 5 minus 3. These numbers are the three components. I believe the first component is 4, is that right? Second component is negative 6. I did something wrong.
Yeah, it shouldn't. It should be 3 minus negative 5.
Yeah, the third component is wrong. 3 minus negative 5. So third component is 8, is that right? I think that's right. Okay, a question like that is easy as long as you know what's going on. But I really hope you can imagine the length is hard to imagine, but at least you can try to imagine the direction. Okay, in x direction is positive, in y direction is negative, in z direction is positive. It's kind of something like this. In x direction is positive, in y direction is negative, right? X direction positive, and then y direction negative. Z direction is also positive. It's kind of that way, if you know what I mean. Okay, in any case, you you just need to know it's kind of similar in 3 space. In the space, a vector has 3 components. Okay. I think we have time to finish at least 1 or 2 questions. We'll work on question 4 together. Okay. We'll do question 4 together. Okay. In question 4, you're given a vector u. You're not given the initial or terminal point. But in 4a, I want you to sketch the position vector u. So you know u is a position vector. Okay. Position vector is a vector with the initial point, the origin. Okay. Now we're going to do the questions one by one. To do 4a, position vector. So the vector u has initial point, the origin. Okay. If you know it's a position vector, if you know u is a position vector, if you know the components of u, you know 2, 1 is the coordinates of the terminal point. Okay. So the terminal point has x coordinate of 2 and the y coordinate of 1. Right. If I want you to sketch the position vector u, I think your vector is something like this. So that's your vector u. That's the answer to question A. Okay. Easy, right? So just ask me if you have any questions. I can go over things in more details if you have questions. I think this part is simple. So just too many terms to remember, too many names. Right? Okay, now look at B. In question B, if the vector B has terminal point, In question B, I give you the terminal point. I give you the components of V. I give you the terminal point. We're looking for initial point. Of course, you can guess. It's not hard to guess at all. Okay, but I will show you a proper way to do question B. Okay. In many cases, if you are solving some unknown, we solve some equations, right? In question B, we are looking for initial point. Okay. So now let's say, now let P be the initial point. Again, I know it's easy to guess, but I'm trying to show you a proper way to do it. So just in case you have more complicated questions, it's easier if you use a proper way. I mean, okay. Now can I use x1 and y1 for the coordinates of initial point? Okay, I'm going to use p x1 y1 be the initial point of V. You see, you know the components of V, you know the terminal point of V, and then we have a formula for computing the components in terms of the coordinates, right? So we have something like this, and then we have so this time the components of V 2, 1 is represented using the initial and terminal points using terminal points are 1, 1, right? Using 1, 1, the x coordinate of the terminal point minus x coordinate of initial point, so which is x1, right? Later on, we are going to solve the equation for x1, y1. Likewise, the y coordinate of the terminal point is 1 minus y coordinate of the initial point is y1. You remember two vectors are equal if they have the same components, the corresponding components are equal. From this thing we have a system of equations. Now let's say 1 minus x1 is equal to 2 and 1 minus y1 equals 1, right? Solve the equation for x1 and y1. Super easy, right? So I have x1 equals, I think -1, is that right? All of you guys know how to solve the equation for that. x1 is equal to -1. x2 is equal to what's that? Sorry, it's not x2. I'm looking for y1. So anybody want to tell me y1 again, please? I think y1 is equal to -1 as well.
That would make y.
Yeah, sorry.
That'd make it 2, wouldn't it?
Yeah, sorry. I think I copied something wrong. The second equation in here should be the second equation here should be 1 minus y1 equals 1. Is that right? So y1 is equal to 0. I think y1 is equal to 0. So by that we mean point P has the coordinates of -1, 0. So we have the initial point P, right? On the screen you have the complete solution to question B. Again, it's super easy to guess. So in this case, you know the coordinates of the terminal point. It's easy to guess the coordinates of initial point, right? And then in question C, we're trying to sketch V. Okay. In question C, we're trying to sketch V. We know the initial point. We know the terminal point. Initial point is -1. -1 is here. -1, 0. So that's initial point. And terminal point of V is 1, 1. I think 1, 1 is here. That's how you sketch the vector V. I think I got the notation right. Okay. So this part is the answer to question C. And then what is the relation between U and V? What is the relation between U and V? They are equal, right? The relation I'm looking for is now I'm going to write the answer to question D. The answer to question D, I will squeeze it here. The relation is U is equal to V. U and V are equal. And algebraically and geometrically, so geometrically you see they point in the same direction, having the same length. And by the way, I think a more proper term is length. Distance is between 2 points, right? They have the same length. Geometrically, no, algebraically they have the same components. You see they have the same components. U to 1, the two components of U is to 1. The two components of V is also to 1. Okay.